Golden Iris Productions presents The Hidden Rhythms of the Hydrogen Atom, Wave Structure, Quantized Motion and Photon Emission by Mark F. Dennis. Part 4. Abstract. The development of modern atomic physics emerged from a sequence of foundational discoveries spanning the electron, proton, quantized radiation and matter-wave duality, beginning with the identification of subatomic structure by J. Thomson and Ernest Rutherford, and culminating in Bohr's quantized atomic model. A new framework of discrete energy states replaced the classical continuous description of matter. Concurrently, Planck's resolution of the ultraviolet catastrophe introduced energy quantization through E equals h nu, later extended by Einstein's photon hypothesis, establishing the quantum nature of electromagnetic radiation. De Broy's matter-wave theory further unified these developments by proposing that all matter exhibits wave-like behavior governed by lambda equals h over p. This work presents a consolidated historical and theoretical foundation of quantized atomic structure, emphasizing the emergence of discrete electron shells, standing wave conditions, and photon emission as interconnected consequences of wave-particle duality.
The early 20th century transformed our understanding of matter. J. Thomson's discovery of the electron revealed that atoms were not indivisible, but contained internal structure. Ernest Rutherford's scattering experiments then established the existence of a compact, positively charged nucleus, fundamentally reshaping the atomic model. Yet classical physics could not explain why orbiting electrons did not radiate energy and collapse into the nucleus, nor could it account for discrete atomic spectra. Max Planck introduced the revolutionary idea that energy is exchanged in discrete packets, expressed by the relation E equals h nu. Together, these discoveries laid the conceptual foundation for the emergence of quantum theory. Building on these developments, Niels Bohr proposed in 1913 that electrons occupy discrete quantized orbits around the nucleus. Each allowed orbit corresponds to a fixed energy level, preventing the classical instability problem. When an electron transitions between these shells, it emits or absorbs a photon whose energy matches the difference between the two states. Louis de Broy later provided the deeper physical explanation by proposing that electrons possess wave-like properties. In this interpretation, stable electron shells arise because only standing matter waves that close consistently around the nucleus are allowed. Quantization, therefore, emerges naturally from resonance conditions imposed on the electron's wave structure.
Karl Schwarzschild's exact solution to Einstein's field equations revealed that gravity alters the flow of time through space-time curvature. This work established that massive bodies reshape temporal structure itself. Extending this idea, we ask whether strong electromagnetic confinement at atomic scales can produce a similar effect. By mapping gravitational terms to electromagnetic analogues, hydrogen can be interpreted as a coupled spatio-temporal resonator.
Quantum transitions and photon emergence from standing wave reconfiguration. From the wave-based perspective, a quantum transition between atomic shells can be understood as a reconfiguration between two distinct standing wave states of the electron. When the electron transitions from a higher energy level to a lower one, the system must shed the excess wave structure required to satisfy the boundary condition of the initial state. This change is not arbitrary, it is quantized and corresponds to a discrete modification of the allowed standing wave configuration of the electron.
Photon as the mediator of wave structure change. In standard quantum mechanics, this transition is accompanied by the emission or absorption of a photon, whose energy matches the difference between the two quantized energy levels. The photon is not interpreted as a lost de Broy wavelength, but rather as the mechanism through which conservation of energy and momentum is maintained during transitions between eigenstates of the hydrogen atom. Within this framework, the process can be viewed as a reconfiguration of a constrained wave system. The electron's matter wave must continuously satisfy a self-consistent boundary condition, and transitions between shells require a redistribution of this constraint across the electron field system. The photon emerges as the quantized carrier of this redistribution, ensuring that total system conservation laws are preserved.
Unified quantization principle. Thus, both the bound electron wave and the emitted photon arise from the same underlying quantization principle, one expressed as spatially confined standing wave modes, the other as freely propagating electromagnetic radiation. Standing wave interpretation of shell transitions. Within this formulation, the hydrogen transition n equals 2 to n equals 1 can be interpreted directly as a reduction in standing wave complexity at the Bohr scale. Each shell corresponds to a quantized de Broy mode satisfying the condition 2 pi r sub n equals n lambda sub n. At n equals 2, the electron occupies a two-wavelength standing mode around the orbit. At n equals 1, the system collapses into a single wavelength ground state configuration. The transition therefore corresponds to the loss of one full standing wave cycle from the bound system.
Energy-based derivation of the photon. To connect this wave interpretation to measurable radiation, the standard hydrogen energy level structure is used. E sub n equals minus 13.6 electron volts per n squared. For the transition n equals 2 to n equals 1, delta E equals E1 minus E2, or delta E equals minus 13.6 minus 3.4 equals 10.2 electron volts. Converting to SI units, delta E equals 10.2 times 1.602 times 10 to the minus 19, or delta E approximately 1.634 times 10 to the minus 18 joules. Lyman alpha photon. Result, lambda gamma, approximately 1.216 times 10 to the minus 7 meters, which is 121.6 nanometers. This wavelength lies in the ultraviolet region of the electromagnetic spectrum and corresponds to the Lyman alpha transition in hydrogen. Physical interpretation. In this framework, the quantum transition is not merely an energy level jump, but a structural reconfiguration of the electron's standing wave state. The reduction from a two-wavelength orbital mode to a single-wavelength mode results in the emission of a photon that carries away the precise energy difference between these quantized configurations. The photon therefore emerges as the physical manifestation of the mismatch between two allowed matter-wave eigenstates, ensuring conservation of energy, momentum, and wave structure across the transition.
Unified wave interpretation of quantum transitions. Physical interpretation in the wave framework. In this formulation, an electronic transition between hydrogenic shells is interpreted as a reduction in allowed standing wave complexity of the electron's de Broy configuration. For the transition n equals 2 to n equals 1, n equals 2, two de Broy wavelengths fit around the orbital circumference. N equals 1, one de Broy wavelength fits around the orbital circumference. The transition therefore corresponds to a reduction in the number of allowed standing wave modes. The missing component of the higher state wave structure is not destroyed, but is re-expressed as a propagating electromagnetic mode. The system transitions from a closed boundary condition, bound electron wave, to an open boundary condition, free photon propagation at C, while preserving total energy and momentum. Thus, the emitted photon is not arbitrary. Its wavelength is determined by the difference in allowed wave modes of the bound system.
Wave structure interpretation of photon emission. When the electron transitions between shells, the hydrogen atom undergoes a quantized reconfiguration of its allowed de Broy standing wave structure. The change in boundary condition between eigenstates produces a discrete energy release, carried by a photon, whose wavelength is lambda gamma equals 121.6 nanometers. This corresponds to the Lyman alpha transition in hydrogen and represents the conversion of a bound matter wave mode into a propagating electromagnetic wave.
Wave kinetic formulation without energy units. The transition can be derived without reference to electron volts by using only electron mass and orbital velocity. Each state is defined by the kinetic energy of its associated matter wave. E sub n equals a half me v sub n squared for the n equals 2 sub n equals 1 transition, using electron mass me equals 9.11 times 10 to the negative 31 kilograms, v1 equals 2.187 times 10 to the 6th meters per second, and v2 equals 1.094 times 10 to the 6th meters per second. The energy difference is delta E, approximately 1.634 times 10 to the negative 18 joules. The emitted photon satisfies E sub gamma equals hc divided by lambda gamma, and lambda gamma equals hc divided by delta E. Lambda gamma approximately 1.216 times 10 to the negative 7 meters, or 121.6 nanometers.
General standing wave constraint. Each Bohr state satisfies the quantization condition. 2 pi Rn equals n lambda n. For the hydrogen atom, n equals 1 standing wavelength around orbit. N equals 2 standing wavelengths. N equals 3 standing wavelengths. Thus, transitions correspond to discrete changes in allowed standing wave topology. Time dilation modified wave energies. Extending the wave model, each shell is assigned a relativistic time dilation factor gamma n, representing a modification of the electron's internal proper time evolution. The effective energy of each state is written as EFFN equals a half me times v squared n divided by gamma n, where the time dilation factor acts as a modulation of phase evolution within the bound matter wave. The shell-dependent values are gamma 1 equals 1.0000266215554, gamma 2 equals 1.0000066552891, gamma 3 equals 1.0000029578896, gamma 4 equals 1.0000166380987,
gamma 5 equals 1.00001064833736, gamma 6 equals 1.000073947003.
Two-state transition with relativistic correction. For transitions such as n equals 4 to n equals 2, the emitted photon arises from the difference between two spatial temporal eigenmodes. Delta E equals 1/2 me v squared sub 2 over gamma sub 2 minus 1/2 me v squared sub 4 over gamma sub 4. This energy difference is emitted as a photon satisfying E gamma equals hc over lambda. Interpretation of the hydrogen spectrum. In this formulation, the hydrogen spectrum is understood as a hierarchy of coupled spatial and temporal wave modes. Spectral lines arise from the reconciliation of discrete spatial standing wave structure, de Broy modes, shell-dependent temporal scaling, time dilation factors. Electron transitions therefore represent simultaneous changes in spatial wavelength configuration and internal proper time evolution.
Unified interpretation. Photon emission is not treated as an independent entity, but as the natural consequence of reconfiguring a constrained matter-wave system into a free electromagnetic mode. Each spectral line corresponds to a transition between quantized eigenstates, defined jointly by spatial resonance and temporal scaling constraints. Conversion from de Broy wavelength to photon wavelength. The de Broy wavelength describes the wave nature of a moving electron. It is given by lambda sub dB equals h over me times v, where h is Planck's constant, me is the electron mass, and v is the electron velocity.
Electron wave energy in a bound state. The kinetic energy associated with the electron's matter wave can be expressed in terms of momentum p equals h over lambda. E equals p squared over 2me equals h squared over 2me times lambda squared. Each allowed shell, n, corresponds to a quantized standing de Broy wave with wavelength lambda n, giving discrete energy levels nn. Energy change during a quantum transition. When an electron transitions between two shells, for example n equals 4 to n equals 2, the energy difference is released as a photon. E gamma equals E4 minus E2. The photon energy is related to its wavelength by E gamma equals hc over lambda gamma. Solving for wavelength gives lambda gamma equals hc over lambda gamma.
Interpretation in the de Broy photon framework. In this interpretation, each electron shell corresponds to a standing de Broy wave. A quantum jump represents a reconfiguration of these standing waves, and the photon is the emitted energy difference between two quantized wave states. Worked example, n equals 4 to n equals 2 transition in hydrogen. The observed wavelength for this transition, Balmer series, is lambda gamma approximately 486.237 nanometers. Photon energy, E gamma equals hc divided by lambda gamma. Substituting values, h equals 6.626 times 10 to the minus 34 joule seconds. C equals 3.00 times 10 to the 8 meters per second.
lambda equals 486.237 times 10 to the minus 9 meters, yields A gamma approximately 4.09 times 10 to the minus 19 joules.
Energy difference interpretation. E gamma equals E4 minus E2. This shows that the emitted photon energy corresponds directly to the difference in de Broy wave energy between the two quantized electron states. Summary. Electron states are modeled as standing de Broy waves, lambda dB equals h over mev. Each shell corresponds to quantized wave energy, E equals h squared over 2me times lambda squared. Quantum transitions release energy differences, E gamma equals EI minus EF. Photon wavelength emerges from this energy difference, lambda gamma equals hc over E gamma.
Conceptual note. This framework does not replace standard quantum mechanics, but re-expresses electron transitions in terms of changes between quantized de Broy wave states. The photon is interpreted as the measurable consequence of this wave state transition. Conclusion. Wave matter transition, de Broy structure, and time-dependent emission. Within the wave mechanical framework developed here, the hydrogen atom is understood not as a set of classical particle orbits, but as a hierarchy of quantized de Broy standing wave states. Each Bohr shell corresponds to a stable resonance condition in which the electron's matter wave satisfies the boundary requirement. 2 pi Rn equals n lambda n.
In this picture, the quantum number n does not merely label an orbit. It defines the number of allowed de Broy wavelengths that can exist coherently around the nucleus. A transition between shells therefore represents a direct change in the allowed wave structure of the electron. When an electron undergoes a quantum jump from a higher shell, Ni, to a lower shell, Nf, the system must reduce its standing wave configuration. The difference between these two resonant states corresponds to the removal of one or more de Broy wavelengths from the bound system. That lost wave structure is not destroyed. Instead, it is released into free space as a propagating electromagnetic mode, a photon. From this perspective, the emitted photon is the physical carrier of the wave mismatch between two quantized matter wave states. Its wavelength is not arbitrary, but is set by the difference in allowed de Broy resonance conditions between the initial and final shells. The hydrogen spectrum therefore emerges naturally as a map of wave structure differences within the electron's bound state.
A deeper refinement of this picture arises when the shell-dependent time dilation factors are included. Each Bohr state carries a slightly different effective temporal scaling, gamma sub n. These factors indicate that the electron's internal phase evolution is not identical across shells. In the ground state, where confinement is strongest, the effective proper time rate differs slightly from that in higher, more extended states. As a result, each de Broy wavelength is not only spatially defined, but also temporally modulated through its shell-dependent phase rate. This means that when a transition occurs, the emitted photon encodes two pieces of information simultaneously. Spatial wave difference, the change in the number of de Broy wavelengths between shells. Temporal phase difference, the change in internal time dilation between the two states. The photon wavelength is therefore shaped not only by the energy difference between levels, but by the combined effect of spatial resonance and relativistic temporal scaling.
transitions originating from lower shells, where time dilation is slightly stronger, carry a subtly different phase contribution than transitions from higher shells, where temporal effects approach unity. This provides a natural interpretation of spectral structure as arising from both wave geometry and local relativistic timing within the atom. Putting this together, the hydrogen atom can be viewed as a coupled spatial-temporal resonator. The electron exists only in discrete standing wave configurations that satisfy both spatial closure of the de Broy wave and internal consistency of its shell-dependent temporal evolution. A quantum jump represents a reconfiguration of this coupled system. One de Broy wavelength is removed from the bound state, and the associated change in phase structure, modulated by the difference in gamma n, is emitted as a photon. That photon is the observable signature of the atom's attempt to preserve both wave continuity and relativistic consistency during the transition. In this unified view, light is not merely emitted by electrons changing energy levels. Light is the direct consequence of a constrained matter wave reconfiguring itself across discrete spatial and temporal eigenstates. The hydrogen spectrum thus becomes a record of how matter waves reorganize themselves under quantization, with each photon carrying away not just energy, but the precise mismatch in wave structure between two relativistic standing wave states of the electron.
To be continued.